All right. So yesterday we talked about reaction arrow pushing. We're going to be using reaction arrow pushing all year long. The one topic I did really want to emphasize from this section, though, was about rearrangements and carbocations, because we're going to see a lot of that this coming chapter. So like I said, the first thing you should always look for is the carbocation identity. So for example, the carbocation on the left was a primary carbocation. How did we know that? It's only bonded to one other carbon, right? That means it's primary. The one on the right, after we do the 1,2 hydride shift, is a tertiary carbocation. Like I said down here, carbocations have the stability trend, right? So tertiary carbocations are much more stable than primary, which are much more stable than, tertiary is more stable than secondary, which is much more stable than primary, which is much more stable than a methyl carbocation. We saw too that sometimes instead of having a hydride shift, you can have an alkyl shift where a next door alkyl group will actually slide over to that carbocation. But the key trend here is that you will only undergo a rearrangement if you can form a more stable carbocation. So let's make a note. And that note is assume that if a rearrangement can occur and it will form a more stable carbocation, then it will occur. Oops, let me clean this up. That it will occur. The actual reality behind this is it does get fairly complicated. Sometimes it's a statistical distribution of rearranged products and unrearranged products. But as far as I'm concerned, if rearrangements can give you a more stable carbocation, assume that it will happen and show your reaction arrows appropriately. All right. There's another thing too I wanted to get into, and that's single-headed arrow pushing, which shows up on sapling. And we talked about single-headed arrows briefly yesterday. What do they normally indicate? One electron, not two electrons. And normally they're used either in radical reactions or for homolytic bond cleavage. And with homolytic bond cleavage, it means that one electron in a bond is getting shoved over to one atom. So for example, maybe one of these covalent bonded electrons goes over to the right oxygen. The other one's going to get hooked over to that left oxygen. And when this happens, you will have an oxygen with an incomplete octet and an unpaired electron. And anytime you have an unpaired electron in an organic system, this is referred to as a radical. Like a Ninja Turtle. It's got an unpaired electron. Man, that dates me. Nobody even laughed at that one. All right, somebody giggled at least. I got that going for me. All right, so single-headed arrows we'll cover a lot when we get into radical chemistry, but for the time being, we're only really going to be using double-headed arrows. So if you do see questions on sapling referring to radicals, you should immediately think, I need a single-headed arrow. Don't be confused and use a double-headed arrow. All right. Yesterday, somebody asked me a really good question about carbocation stability. They said, why is this the case, or should I just accept this on blind faith? That's what we're going to cover today, is essentially why tertiary carbocations are more stable. So this is due to something called hyperconjugation. It's a pretty interesting phenomenon that is invoked when we talk about carbocation stability. And let's actually go back and talk about resonance briefly, because that'll never go away. Resonance is often called conjugation too. Not exactly, right? So conjugation isn't the same thing as hyperconjugation. It's got a different prefix. Not exactly. You'll see the difference. So if we think about resonance, right, we could look at carbocation stability in a resonance stabilized system, and we could say, well, this carbocation is unusually stable because we have a resonance structure where we can delocalize that positive charge across the far left and far right carbon. In fact, this is a very, very stable carbocation. So this is stabilizing. Hyperconjugation is a little less stabilizing, but it's along the same lines. And so I'm just going to box this off so we can compare. Hyperconjugation is the interaction of an sp3 lobe with a neighboring carbocation. Whoop. Actually, let me change this to say stabilizing interaction. The hyperconjugation. Now let me clear this up. All right, so I'll show you an example of what this looks like from an orbital point of view. Okay, so let's say we've got a methyl group right next door to this carbon, and this carbon is just going to be connected to some generic R groups. We don't really care what those are, but this carbon has a positive charge. So it's a carbocation. Over here, we've got a methyl group that is sp3 hybridized, right? So let's try to draw a little bit of the orbital picture. And if we draw the orbital picture, this center carbon has an empty p orbital, right? Because it's sp hybridized. So I'm going to go ahead and draw in an empty unhybridized p orbital. And then the methyl group that's right next door, we said is going to be sp3 hybridized. I'm not going to draw all of the sp3 lobes because that's just a pain. I'm only going to draw one of them, and hopefully you'll get the idea. So each one of those hydrogens is covalently bonded to a carbon through an sp3 orbital overlap. So for example, we'll show this top carbon as an sp3 lobe. And then we'll show our hydrogen up here like that. And so we've got this sp3 hydrogen overlap, right? What occurs in hyperconjugation is basically this orbital will share some of its electron density with that empty p orbital. If you think about a pi bond, right, it's a similar idea in resonance, but that is two overlapping, or parallel p orbitals sharing electron density, right? In this case, it's actually the interaction between an sp3 lobe and a p lobe. So it's not as strong or as stabilizing as a true p orbital overlap. So let's make a note of what's going on here. And empty p lobe. And I did want to note that this is not as strong as resonance. Oop. I'm not spelling right today. Oh my goodness. This is not as stabilizing as p orbital interactions. That we see with resonance. Resonance is much more stabilizing than hyperconjugation, which seems counterintuitive. Why use the prefix hyper if it's weaker? But that's just what they call it. Yeah?
I assume because of the electron deficiency that this would be a very conductive material.
No, not necessarily. It's very reactive. It's not happy having a positive charge, but we wouldn't refer to it as a good conductor either way because typically these are very short-lived. They want to react with anything to neutralize that positive charge. Good question, though. All right, so let's make a general trend. So the general trend is that if you have resonance, stabilized carbocations, they are the best. And you saw an example of one of those previously. These are better than tertiary, which are better than secondary, which are, again, way, way better than primary. In fact, you almost never see primary carbocations that exist for more than a tiny fraction of a second. And this is way, way more stable than a methyl carbocation. So increasing stability. And some people were asking me the other day, what the heck do you mean by methyl? And so I wanted to clarify that a little bit. If you think about a methyl carbocation, it's not attached to any other groups. So instead, what it is something that looks like this. So it's CH3, not CH4. And it has a positive charge. Why do you think this isn't very stable? It doesn't have a full octet, and it doesn't have any neighboring sp3 lobes to help stabilize that carbocation center, right? So no electron density can be dumped into that empty orbital to help stabilize it in any way, shape, or form. So these are incredibly unstable. So I did want to briefly clarify that. All right, I think that's where we're going to end off today. Tomorrow what we're going to do is we're going to start a new chapter and get into substitution chemistry. But make sure that you finish your sapling tonight. It's due tomorrow.